In class, we've been discussing physical quantities, things that can be expressed using this number, a magnitude, and a unit. Well, there are two basic types of physical quantities, those which we call a scalar quantity. And a scalar quantity is one that has magnitude only. It does not have direction. So as an example of that, mass, speed, energy, things where it would have no meaning whatsoever to try and give a direction. The mass, 5 kilograms. It would not mean anything to say 5 kilograms upwards. Speed, simply how fast one is going. Energy, so many joules of energy. You can't give energy a direction. Other examples might be volume, so many cubic meters, or perhaps density, so many kilograms per cubic meter, that sort of thing. Magnitude only. You need to know the definition of a scalar quantity. In contrast, then, a vector quantity is one that again has magnitude, but as well as having magnitude, we also have direction, and direction has meaning in terms of a vector quantity. So here are some examples of vector quantities. Displacement. The scalar equivalent of displacement would be distance, whereas the vector is saying how far, 12 meters, but also giving a direction upwards here. Velocity. We talked about speed being a scalar, but if we start giving it a direction, it could be to the right, it could be downwards, it could be 20 degrees east of south or something like that. That then becomes a vector. Acceleration, vector. Force. We give force usually a direction. Direction matters, and so that's a vector quantity. Important to realize then that vectors cannot be described fully unless their direction is stated as well. So if you're going to quote an answer to a calculation for a vector where direction has come into the thing, then you need to state direction. One particular case is weight. Now, people often confuse weight and mass, but technically weight is the force due to gravity, and because it's a force, then it is a vector quantity. You often don't give the direction with weight because simply it's downwards, but that is sort of implied in the understanding of what we mean by weight. Right, this page here, there's not a lot from this page that I actually want you to draw into your notes. Simply the fact that if we've got a vector which has this magnitude and has direction, we can represent a vector quantity with an arrow. In maths, you use column matrices or to represent a vector. Here, we do the thing diagrammatically. Okay, and so here are a number of examples of vectors. We've got an arrow drawn to a particular length, representing using a scale, representing then the magnitude of the vector, 15 kilometers, a bit shorter, 25 kilometers, a bit longer, etc. And then by putting in the angle, we're able to specify the direction. In terms of your notes from this page, I simply want you to write down that statement there about the arrow. I'd like you then to draw, well, I think we almost could draw a new diagram here rather than even using one that's there. Draw an arrow without all that sort of bit in there. Just simply draw an arrow, give it a direction. Let's use 60 degrees again, and let's label the magnitude. Let's make it 20 kilometers, but we haven't got this extra little bit down the bottom here. That's probably not so helpful. Just draw that diagram there. And the other thing we need to know about this vector is that we call this the head of the vector, and we call this the tail. Now, I've said about these being drawn to scale, but often you don't necessarily draw vectors to scale. You simply draw a diagram, and when you've labeled things, you take the label, for example, 20 kilometers, as being an indication of the length of or the size of that particular vector. So sometimes it's appropriate to draw something to scale. Sometimes something just drawn relatively neatly is all that's needed. All right, addition of vectors. Now, when we add vectors, vectors have got a direction. Then when we add those vectors, the direction of those vectors matters. So we've got a few simple examples here. Two vectors of 5, there might be 5 Newton forces, for example. It could be 2 velocities, 5 meters per second. When we add those vectors together, we get 10. But if they were in opposite directions, 2 forces, one force, let's say, pushing one way and one force in the opposite direction, when they add, we get 0. Similarly, adding here, we get 15, adding here, taking direction into account, we get -5, the negative indicating that the vector is towards the left as opposed to the right. So the important point here is simply to take note of the point at the top that with addition of vectors, when adding them, the direction of vectors matters. That's all you need in your notes. Right, addition of vectors. Here's an example. I'd like you to copy this example into your notes books. The first couple of questions I think you could answer fairly easily. So if the two forces of 500 newtons are in the same direction, and I think we could simply say 500 newtons plus 500 newtons equals 1000 newtons, easy. If they're in opposite directions, well then those two opposing forces are going to produce what we call a resultant of 0 newtons. Now the question really is what happens when you've got vectors at other angles. So what I'd like you to do is leave a bit of space and we will go through those couple of examples together in class. So I'd suggest you probably want to leave, I'd say, about half a page for that, and we'll come back to that and perhaps talk it through together, I think. Okay, right, so just general principles then of what happens when we add vectors together. Vectors are added head to tail. All right, so we talked about the head, we talked about the tail. So here we've got in this diagram on the left here, two vectors. One vector I've labeled simply B, one vector I've labeled A. So that vector could represent a force, it could represent a velocity, it could represent something called momentum, which we'll study a bit later in the course. Anything that's a vector quantity could be represented here. Take note that at present, the way the diagram is drawn, the two vectors are tail to tail. So that does not show the addition of those vectors. You do not add them by drawing an arrow across here in some way. To be able to add those vectors together, we draw one of the vectors. I've chosen to draw vector A first. So I've taken that vector there, transferred it there, and then I've taken vector B and I've added head to tail. If I want then to get what the sum of those two vectors is, what we get by adding them, that sum is called the resultant, and we draw that from the tail of the first to the head of the last. And I've put, in this case, a double-headed arrow to indicate the resultant. You don't have to do a double-headed, it could be a single, but that's the type of diagram that you get. All right, so the sum of the vectors is called the resultant. So in terms of your notes, I want you to basically write down everything that is on that page there, please. Just take note that the left-hand diagram here shows what we did on the previous page. The right-hand diagram over here shows me adding the vectors together using the opposite order. Vector B first, followed by vector A, added head to tail. The resultant is exactly the same in both cases. So we can conclude that when we're adding vectors together, the order of addition does not matter. We get the same resultant. So in terms of your notes, you could just draw this right-hand one here and take note of this point at the bottom. All right, what happens if we've got more than two vectors? Here we've got three, A, B, C, all drawn here with their tails together, but that's not how we add them. We add them head to tail. So I've chosen randomly to draw vector B first. I've then taken vector C, added it head to tail. I've then taken vector A, added it head to tail, and my resultant goes from the tail of the first vector to the head of the last vector. So that's my resultant there. Now, for this one here, it probably is worth your drawing those diagrams in your notes, I would say. There is a method called the parallelogram of vectors, and that I'll just mention it. I don't think I want you to write this in your notes. I'll just mention it in passing that it is possible when you've got these two vectors A and B drawn like so to simply create a parallelogram, and what that and then draw the resultant in here as the diagonal for that across that parallelogram. Effectively, what you have done is again added vector B and vector A together, but it's a slightly different approach to doing it. So that's just to mention it in passing without you drawing that